Hello. Today we'll be talking about segment lengths in circles, which is really kind of a lie, because what we're really going to be talking about is the ratios of segment lengths. When it comes to actually computing the length of a chord, we don't actually have any formulas for that. And before we work the problems, I'll try to quickly show you why we don't have formulas for that. Formulas do exist. They're just more than what this class would cover. So that's why we're doing things that might seem kind of weird if you think about it. I mean, it says segment lengths in circles, and throughout this section, at no point are we going to, say, draw a chord and then say that given a radius and the arc measure that chord covers, we should be able to figure out the length of that chord. And in fact we can, but it's really hard to do with the information we have in this course. So let's start doing what we can do, and that is pointing out the ratio relationships, for instance. And this should look kind of familiar to you. AE times EB is the same as DE times EC. In other words, when these things intersect inside the circle, they get broken up into similar segments. Remember that from our triangles. And there's a way pretty easy to see that this is true. And by the way, in this section, I'm writing all the theorems this way. You can, in English, say something like the product of AE and DB is the product of DE and DC. It goes on and on and on. This is a big, long English word paragraph. And, well, I guess you have to do that sometimes so people know what the heck you're talking about. But the fact is, this is a math class. And ultimately, all you should ever really need is equations. I admit we don't just do equations in high school geometry, but too much verbiage, in my opinion, is too much verbiage. I would never ever be able to remember a theorem if I had to read the whole 2-paragraph English version. But I could remember this, and you can too. This is just the mathematical statement of what's a big paragraph. It's a couple other theorems I'm going to show you. They have even more verbiage if you want to go look up the English word version of it. But English words are pretty clumsy in mathematics. That's why we have equations. Anyway, the reason that this would be true is pretty easy to demonstrate. Well, suppose we connect up these endpoints. So we create a couple of triangles. If we can show that these two triangles are similar, then we automatically have all this stuff right here. Well, what reason would there be to say that these two triangles are similar? We could start with this. Look at the arc DB. We have an inscribed angle which intercepts the arc DB. That's this angle here. Call it ECB. Well, what about this angle? Call it EAD. It also intercepts the arc DB, and it's an inscribed angle. Well, from what we know from previous sections, two inscribed angles which intercept the same arc have to be congruent. So there's two congruent angles. Now these form a vertical angle pair, so we know from way early in the class that these have to be congruent. Now we're not going to show that these triangles are congruent, of course, but now that we have two angles, this is our angle. which tells us that these two triangles are at least similar. Well, they definitely are similar. It doesn't preclude them from being congruent, but you can't really say that yet. And in this case, you definitely can't say that. But they are similar. And remember, it's really easy to show that all the angles are the same because they have to add up to 180. So if this angle is the same as this and this one's equal to this, what's left over has to be the same in each case. These are each 180 minus this stuff. This one here is 180 minus the other two. This one is 180 minus the other two, which are both equal. So it's very easy to say that the other two angles, which are just have to automatically be congruent, there's no way around it. Well, now we have AA is good enough. And AA automatically leads to AAA. So we've got AW automatically leads to AW. Well, and that's all we had to do. Now we know that these two triangles are similar, and we can match up the corresponding sections or sides. For instance, the ratio of AE to CE, and that's, or I guess I should have written this a little differently if I'm going to prove it this way. This leads to a couple of different ratios. Naturally, with a 50-50 chance, I grabbed the wrong one. I should probably rewrite that so it makes more sense in terms of this actual diagram. Now doing it this way matches up a little better. Neither one is incorrect. As you well know, we can say multiply by 1 over DE on each side, or we can multiply by 1 over EC on each side. They lead to two separate but equivalent ratios. But writing it this way, it's more demonstrative of what's actually going on, which is this segment here and this segment here aren't exactly the same ratio of the other two. I would say, in other words, this segment, these two corresponding segments are in exactly the same ratio as these corresponding segments. I could also write that this ratio equals AD over CB, but that wouldn't tell us anything with respect to this theorem. So the important result here is that when these things intersect inside a circle, what we do is end up producing similar segments which are multiples of the other segment. Because after all, this ratio is just some number. We don't know what it is, but we can always write it as, just some number, call it R, some real number. Well, that means that DE equals R times EB, or EA equals R times EC. Just like we did with similar triangles, this would be the scale factor. Same thing here. Now this is call it the secant segments theorem, or segments of secant theorem. At any rate, if you check it out in your book, it's just a whole bunch of words. I mean, it's big. And all it really says is this right here. This line, it all comes down to this. Very similar to the theorem we just saw. In fact, if you prove it, you do exactly the same thing. You work out a way to draw yourself some similar triangles. And what kind of triangles you want to draw is kind of obvious from the relationships you're trying to come up with. In this case, we have that EA times EB, which is not the segment times the segment, it's the segment times the whole. Same thing down here. The segment times the whole. So that when you rewrite them into ratios, you get the ratios of these two outside segments is the same as the ratios of the entire segment. Except, of course, nothing gets to be easy. They get reversed. By that I mean this first ratio is EA over EC, whereas the second ratio is ED over EB. So the ratios of the entire segments is the same as the ratios of this tiny outside part, the outer segment, except that they're flipped. This one we got this over this. In the other case we got the lower one over the upper one. And you can maybe see graphically how that might work out. Notice that this appears to be shorter than this one. On the other hand, the interior part is longer. And vice versa over here. This appears to be longer on the outside, but that shortens the inside. Well, as I say, in your book, you could memorize the whole paragraph or two if you want, but I think this is the part that I would concentrate on remembering right here. From this, you can always derive this, and naturally, you can always get two ratios out of this. And you could write also EA over ED equals EC over EB, I hope, if I got that right. In other words, multiply by 1 over ED and then multiply by 1 over EB. And then we get that this over this entire length is the same as this short outside segment over this entire length. Whichever one's easiest for you to remember. This, or this, they're all rearrangements of the same equation. So remember the one that fits in your brain easiest, and you'll do great on the test. And this is the analog of our secant segments theorem. If one of the lines isn't a secant but a tangent. And in that case, well, we don't really have any segments to talk about for this upper one, do we? Except for the part between the point of tangent C and the vertex here, this outside angle. That's the only segment we have for this line. So we use it twice. What else could we do? And this theorem, which is the tangent secant segments theorem, or the secant segment, well, you get the idea. It's also got a whole bunch of words that all add up to just this. I like this version better. All we have to do is square this, and the square of this becomes equal to this segment times the whole segment. Very similar to our last theorem, except that there is no extra segment here where it intersects the circle. It just stops right here. So, like I said, we just use it twice. And of course, this line leads directly to this, which is the EA over EC is the same as ED, that's the entire segment here from vertex to the opposite side of the circle, over this segment here. And if we work some problems, these formulas here that are really the result of the theorem, and I would say the important part to remember. I wouldn't worry too much about all the verbiage that goes with these theorems. But before we work the problems, I'm going to show you why we're not really going to, why this book, and hardly any book, tells you much about the actual length of a chord. So that's what I'm going to do next, and it's not going to be on your standardized test. The problems in this book won't use it, which means that it is superfluous to the class that you're taking. If you're curious, you can watch that part. If not, then I would just skip ahead to the problems and don't even bother looking at what I'm about to do next. In this section, even though it's called segment lengths, all they actually tell you about is ratios of segment lengths. They still haven't given you a way to find the actual length of a chord. This would be the chord CD right here. How long is that? Well, it seems obvious you would have to know at least a couple of things, like the radius of the circle would certainly help. This central angle, which would be the same. Remember, we measure the arc that is intercepted by a central angle by the central angle, so that if the central angle was beta, the arc measure would also be beta. What's the length of this chord? Well, I went ahead and drew in a diameter here. Now we know from previous sections that you can always find a diameter which bisects the chord and is perpendicular to it. In other words, a perpendicular bisector of this chord. And then, once we've drawn the diameter, and we have a center here, P, we draw a radius from P to C, and then another one from P to D. That creates initially one triangle. And we know from what we learned about isosceles triangles that the perpendicular bisector of the opposite side is also an angle bisector, which means that this angle from, we'll say, BPC, how about that? That's beta over 2. And this one, DPB, that's also beta over 2. Since we know this is an angle bisector, we just broke up beta into 2 halves. Real simple. Why would we bother to do that? Well, because if we look at these two triangles separately, it's pretty easy to, well, it's easy to see, and it's even easy to prove. These are both congruent triangles. Number one, we've bisected CD, so these two sides are congruent. This is congruent to itself, so that's 2 congruent legs in a right triangle, and that's all you need. What is the length of this side? That's why we broke it up. Now that we've got 2 right triangles, it's be a lot easier to figure out the length, because this is now the leg of a right triangle. The problem is, even if I know the radius, that's not enough to tell me what the leg is. I have to know the other leg, which I don't. Or, if I knew the angle and one part of a triangle, well, that sounds like a job for trigonometry, doesn't it? After all, trigonometry is what relates different sides by their angles. So instead of knowing 2 of the sides, or 2 components, let's say, of because it could be a side and a hypotenuse, instead of knowing the 2 linear components of a right triangle, we could know 1 length and 1 angle, and that would be enough to tell us everything we need to know also. Why? Because we know trigonometry, or at least a little bit of it. And that's exactly what we're going to do. Remember from trigonometry, sine is opposite over hypotenuse. How do we remember that? Remember our mnemonic? Some old hippie caught another hippie tripping on acid. Some old hippie, that's the first letter is for sine or cosine or tangent. The first phrase starts with an S, so that's for sine. Old, that's opposite over hypotenuse. O for opposite, H for hypotenuse. That means that the sine of this angle equals CE over R. So now we can write the sine of beta over 2, remember this is only half of the angle, is equal to CE, that's this segment of the chord, over R, or CE, this part here, equals R times sine of beta over 2. And we know that this diameter bisects CD, so CD is just double whatever CB is. And we can write that the length of this chord is equal to this here. The reason that this isn't mentioned in most high school geometry books is that this equation doesn't really demonstrate anything. None of the ratios that we used, the theorems we have from geometry, this is all just plain trigonometry. The fact is, most of the things that we've done in this course could be done using trigonometry, but trigonometry is, in a sense, almost a separate discipline, in the sense of how complex it is. We could spend easily an entire 3-month college class, which usually covers more material than 3 months in high school. So actually in high school you could easily spend 6 months just on trigonometry. In college it's frequently a 3-month course, sometimes it's a full semester. There's a lot to trigonometry, much more than what we covered. And I'm thinking that that's probably why they don't even bother to tell you how to compute this length. There is a way to do it, and this is it. This won't be, as I said, on your state exam. So I'm tempted to say if you didn't look at this section, it doesn't matter. But if you didn't look at this section, then you're not going to hear me say that, are you? So that was kind of a stupid thing for me to say. Anyway, I just did this for those of you who are curious as to why a section labeled segment lengths doesn't actually tell you how to find the length. Well, this is why. And now let's work some problems that really are germane to this section and the kind that you may well see on your state exam. Now here's a simple application of the last theorem we looked at. All they want you to do is find x. And we just have to remember our tangent secant theorem. And that was that 24 squared equals 12 times the whole thing, which is 12 plus x. So all we have to do is we lay this out. 24 squared is 12 times 12 plus x, because remember, it's not like the segments, the pure segments theorem. This is the secant segments theorem, which is a little bit different. It's this segment times the whole thing, which is written this way. So first thing we can do is divide both sides by 12. 24 times 24 divided by 12, that would be 2 times 24, which is 48. Now we subtract 12 from each side, and we get that x equals 36. Very easy. Now here it looks like a couple of congressmen got bored with taking bribes from lobbyists and decided to mess up a geometry problem. So let's see what they did wrong this time. CD times DF. Well, here's CD, that's this section, times DF, that's this segment, equals AB times AF. Well, we have a secant segments theorem, but it doesn't say this. No, remember it was written like this. FA times the whole thing, that's the outside part, times the entire thing, not just the inside part. That's the difference between the secant segments theorem and the ordinary segments inside a circle theorem. So our second thing here should be FB. That's a stupid thing to say. The second term is what it's called in mathematics. It's not just a thing. It's a second term here, is FB. Well, and over here we got CD times, well, that's not right either. CD's all wrong. FD's okay, that's fine. But it's FD times the whole thing again, FC. Oops. So if we write out the correct equation, we can start punching in numbers and see what happens. For instance, the first thing we can see is that I can't add 3 and 5. Hold on a second. There we go. Normally 3 plus 5 is 8, not 9. So FA, we can just start plugging numbers in here. FA is 3. FB, that's the whole segment. That's 8. And that equals 4 times FD times the whole FC. Well, FD is 4, and FD plus, well, I could substitute 4 in here for this FD also, couldn't I? So if we put that 4 in here, go ahead and distribute this one. We get 4 times 4 is 16 plus 4 times DC on this side is equal to 3 times 8. Well, fine, that gives us the 24 equals 16 plus 4 times DC. We subtract 16 from 24 and get 8. So we have 4 times DC equals 8. And that, of course, will give us that DC equals 2. And it's, I was going to say it's a more sensible answer, but actually, if you just look at it, 3.75 isn't really obviously wrong either, is it? It's still less than 5. If you'd come up with a number like 23, then you could just say that this is wrong, because that would just be silly. I mean, look at how long this is compared to everything else, and if you come up with a number like 23 or 58, you could just say that anybody can tell that's wrong without doing anything. But in this case, even though he did it wrong, the answer he came up with wasn't that far off. But it's still wrong. We're right, they're wrong. Well, it looks like, once again, we need our secant segments theorem. We don't have any labels here, but that's okay. Remember, it's this section times the whole thing, this segment times the whole thing, equals this segment times the whole thing. That's, I think, usually the easiest way to remember it. And then you can rearrange it into ratios if you need to solve the problem. So let's try it that way first. X times the whole, which turns out to be 45. And it turns out we don't hardly have to rearrange anything, do we? X times the whole here, that's x times 45, it's 27, and they give us the whole length. Didn't even have to calculate it. So we just got 27 times 50 over here. Now we just divide through by 45, and according to my calculator, that equals 30. So this part here is 30. And that answer seems sensible. This segment appears to be just a little bit longer than this one, and 30 is just a little bit more. So I think we've got it right. Now here we just have to use our plain old segments theorem, or segments inside a circle. Call it whatever you want. The important part is that the result, which says that this segment times this segment, or the length of this segment times the length of this segment, is equal to the length of this segment times the length of this segment. In other words, when they intersect, they break each other up into similar parts. So let's write that out mathematically. What does that mean? Well, it means that x times x, or x squared, is equal to 2 times 2x plus 6. And I think we can do that in our head without messing up. Maybe. And that's 4x plus 12. So we just write that into our standard form so we can factor it and see which one of these numbers makes sense to us. Well, now we need factors of 12, actually negative 12, that would add up to 4. Well, 3 and 4 don't work. I'd vote for 6 and 2. Like minus 6 and plus 2. It seems to me that would work. Let's try that. X minus 6 times x plus 2. Now let's see, that'll give us a negative 12. Minus 6x plus 2x is minus 4x, and we got x. Okay. That looks like it. That means x could be 6 or minus 2. Well, gee whiz. Looks like we got 2 right answers here. Equationally, anyway, we have 2 right answers, but x is a length. And if we have a coordinate system, minus 2 makes sense. That means 2 units off to the left. But when we're talking about lengths, I don't think minus 2 is going to make much sense for us, is it? It's dimensions, those kind of dimensions, like length, width, weight. Met anybody who weighed a negative 160 pounds? I'm not even sure what that would mean. I guess it would mean you would fire upward with a thrust of 160 pounds. So if you weighed negative 160, you'd be in the stratosphere somewhere, I guess. Luckily, nobody does. And same thing with lengths. Negative 2 makes perfect sense as the solution to an equation. You just have to remember that the solutions to equations also have to match up with reality. And in this case, negative 2 really doesn't match up with reality, so the correct answer is, of course, D, 6. Don't let them mess you up on the test and try to suck you into picking minus 2. It's a legitimate answer for the equation, but it's not a legitimate answer for a segment length. This problem is, it's not that obvious what you would have to do to arrive at the radius. If they'd ask us for something like, say, DC, we'd know just what to do, wouldn't we? So let's find DC here and see what happens. Remember from our tangent secant segments theorem, AB squared, that's this part, is the outside part times the whole thing, or 12 squared equals 8 times 8 plus 6 plus DC. Remember, I have to take the whole thing here, not just the segment. So that adds up to 14 plus DC. So we can divide it through by 8, after we square 12, of course. 144 divided by 8 is 18. DC plus 14 equals 18, then DC is 4. Oh, and yeah, it's given that PD is also 4. Well, okay, so what? We're still trying to find the radius. That's the distance from P to the circumference. It's tempting to draw a line here because we know that'll be perpendicular and try to work out a right triangle somewhere, but we don't have enough other sides of that right triangle for that to work. That would be a red herring. By the way, you know where the expression red herring comes from? When they train dogs to follow a scent, like fox hunting dogs, they'll use red herrings to see if the dog will take off and follow the scent of the herring. If he does that, then he messed up and he still needs more training. A well-trained dog will ignore the scent of the herring and continue on the scent that he's been asked to follow. Hence the name, following a red herring or something like that. Who cares? The point is, now that we know that DC is 4, we have to figure out some way to get at the radius. Well, what else do we know? We know that we've got a center here, and we can draw a segment from the center to any chord, which will bisect the chord and be perpendicular to it. So let's do that. I'll just draw a little dotted line here to indicate I'll try anyway, where we dropped down a perpendicular, which is now a bisector, which means that since we found this, we know that the whole thing here, well, this whole segment EC, has length 10. So if we bisect it, that's 5 on each side, right? On the other hand, this distance is 4. Well, this is the bisector with 5 on each side, so this right in here, this must be 1. It's kind of like we just shifted this over 1 unit. So now we've got this perpendicular line. We have a leg, we can call this a leg of the right triangle. This is a hypotenuse of our new right triangle, and here's another leg, which we haven't found yet. We're going to find this, and then we're going to use that to find something else. Yeah, it's several steps involved here. So our hypotenuse, that's 4 squared, which is 16, is 1 squared plus this stuff. And I'll just call this x for now. Okay, that way I don't have to label this point. 16 is x squared plus 1 squared. Here's the hypotenuse, leg, and the leg. Well, that just means that x squared equals 15, right? 16 minus 1, or x equals the square root of 15. But of course, that's not what we're looking for. We're looking for the radius, which would be the whole thing. But extending this line is not how we're going to figure that out. Now we can write in that x equals the square root of 15. Well, how about we draw another line from the radius to the circumference that meets up right here at C. then we would have another bigger right triangle that goes from PC and then from C to a point here that I didn't label. Maybe I should have done that. Let's just call this F, okay? There we go. PC to CF and then FP. So if I draw that stuff in, this hypotenuse of our new right triangle, well, that's R. Here's the leg, which we just figured out the length of. That was our old perpendicular bisector. And I've labeled this point where the perpendicular bisector hits it as point F, which means that CF must be 4 plus 1, or 5. And this leg here is the square root of 15. So R squared would be the square root of 15 squared plus 5 squared. So let's lay that out and see what happens here. This is getting a little confusing, but remember, in this new right triangle, this is the hypotenuse. 4 plus 1 is our, say, bottom leg here, and our other leg is square root of 15, which is what we just computed when we did this stuff here. So we've got 5 squared. That's the 4 plus 1 part, plus the square root of 15 squared equals R squared. And if I give myself a little room so we don't run off the bottom of the screen here, we now have 25 plus square root of 15 squared is just 15, of course, equals R squared. But 15 and 25 equals 40. So R is the square, gee whiz, what the heck was that supposed to be? The square root of 40, or how else could we write that? We could write that as 4 times 10, and then take the square root, and then it'll give us 2 times the square root of 10. Took a while, didn't it? And by now you've probably forgotten what we did. Remember, we had to use our secant tangent segments theorem. Takes longer to say than it does to write. Which told us that 12 squared was equal to 8 times this whole thing, which of course was 14 plus DC. We used that equation to get this segment here. Once we had that, we knew the whole length of EC. Knowing the entire length allowed us to compute the length of half when we drew in the perpendicular bisector, which we know from previous theorems has to exist. That is the bisector from the radius to the chord. It bisects and it's perpendicular, and we know that that exists from previous theorems. When we drew this, that allowed us to produce a right triangle with this little leg here equal to 1 and this hypotenuse equal to 4, which is why they told us what PD is. PD wasn't a red herring. That allowed us to arrive at x equals to square root of 15. Then we drew another right triangle, and that made it possible to find R, which is just the hypotenuse of our last final right triangle, and that gave us 2 times the square root of 10. Took a while to get there, but if you just slow down and take these things one step at a time, you can eventually end up where you want to be. And that's about it. By the way, if this seemed kind of boring to you, I don't blame you. I like math, and it seemed kind of boring to me too. Remember, I complained about a dentist to a friend of mine who worked at the clinic a long time ago, and she said, "We don't have any bad dentists. but some are better than others. Same with this. There are no topics in Common Core geometry which are trivial or insignificant or not worth knowing about, but some are more important than others. The next section we have is way important, and by important I mean that the kind of thing that you're going to see over and over and over again in science, engineering, math, statistics, anything that involves math, including math itself. If you're going to see it over and over and over again, or at least frequently, I consider that important. If you're unlikely to see it again, well, that puts it on the less important scale. And if you're unlikely to see it again, and it's also not very interesting, that puts it on the even less important scale. But remember, there's nothing in Common Core geometry that isn't important to the people who write the state exams. You got to know all of it so you can do well on your standardized exams. But don't feel bad if you, or don't get the impression that you don't like math if you find parts of it boring. I love math, and I still find parts of it boring. It's just you can't like all of it. I don't think anybody does. The next section is going to be equations of circles. That's very important. You'll hardly find another science, math, or any other engineering, any class that uses math, that isn't going to expect you to understand equations of circles. Well, that's it for now.